Good day, everybody. Justin Miller, Oxford College Physics. We're going to be looking at some more aspects of rotation today. And what we're going to do is just expand on it. There's lots going on with rotation, as was mentioned, so we continue rolling onward. So, we've got ourselves, we looked at just rotation in general aspects of it, angular displacement, angular velocity, angular acceleration. And then we looked at translation of rotation, that is, a rotating object that is allowed to roll across the surface will translate its rotation into a forward motion. That was good. Balls rolling, wheels rolling, whatever you want. Roll it. There we go. We got some translation. Well, there's some other things that we also want to look at that have to do with rotation. And let's just take a look. What happens if I don't have an actual rolling object? What if I have something that's like a point mass here? I consider this to be some point mass, and I start rotating it around. And around it goes, right? It's moving with some angular velocity, has some angular displacement that's occurring over time. There's some angular acceleration if I speed it up or slow down its rotation. But ultimately, we could talk about this just as we talked about a rotating solid object or a rigid object completely. But there's some other ways that we could think about this as well. We could think about, well, how fast is this little point mass actually moving through space? Not in terms of its angular quantity, but a linear type of quantity. And in that, we don't really look at angular, we look at tangential. We look at how fast is this object moving tangent to the path that it's making through space. Now, tangent's just tangent to the circular path that it's making, and we just want to know how fast is it actually moving. So, let's go back to the wheel, a nice solid object, right? And we can kind of focus on one part of the wheel and say, well, how fast is this point right here moving through space if it's rotating? So just its speed, or its tangential speed. How fast is it actually moving? Well, we could start concluding things about its rotation, right? So I could count out a rotation. There's one rotation, two rotations, three rotations, and so on and so on. There's a rotation occurring per unit time. And if I want to know how fast this actual point is moving, well, it's really just the distance that it travels divided by the time interval which it's traveling that distance. If we're talking about an average or if it's traveling at a constant rate. So we'll focus our attention on that for now just to get the idea of it. But ultimately, how fast this point is moving through space is dictated by two things. What the angular rate of rotation is, and the distance that it actually has to move through space under those rotations itself. The distance that it moves in one full rotation is equal to the circumference of a circle. So, just like we had with translation, this object rolls around one complete time and moves forward by its circumference. Well, if this point here moves around one full time, it moves a total distance equal to the circumference of this circular path. So, what can we get from that? Well, there's equivalence with that. We have that the translational velocity is ultimately directly established in the same way that the tangential velocity is. It depends on a time rate of change of angular position and a radius at which the object is undergoing a rotation. We're sticking with circular rotations here. So, what we want to do is sort of put some stuff out here and then see why this is an important quantity. So we can have some axis of rotation. We can have some point mass. That is rotating around with some constant angular velocity. It doesn't necessarily have to be constant, but let's just say we've got omega is equal to a constant rate here. So if we want to know how fast this object's actually moving through space, what does it depend on? Well, it depends on the radius of this circular path that this object will ultimately trace out. And what are we really looking for? We're looking for this. We're looking for this sort of velocity vector, which is the tangential velocity. Well, the direction of the tangential velocity is this tangent to the path that it's making. So the direction we're not super concerned about, other than it's tangential, what we want to know is what is the actual tangential rate? or the tangential speed of the object. So again, this object goes around in one full time based upon what the angular velocity is, and the distance that it travels depends on, well, the radius here. So we think about, again, arc lengths, radii, angular displacements, and we have that the tangential velocity, v sub t, or the tangential speed, is equivalent to r times omega. So this is now tangential speed, which is just how fast it's moving through space. How fast the rotating point is moving through space. All right, so that's kind of that with respect to the tangential speed. But we could also talk about, well, what if this is not constant? What if omega is not constant? Well, we still have at any given moment in time that how fast the object is moving through space is determined by what its angular velocity is at that moment in time and what the radii of its curved path is. So this is at really any given moment in time, regardless of whether omega is constant or changing with respect to time. If omega happens to be changing with respect to time, what do we have then? Well, then we have ourselves an angular acceleration. So if omega is not equal to a constant, alpha is not equal to 0. That is to say, we have now an angular acceleration. Well, if the object's undergoing an angular acceleration, omega is changing with respect to time, which means that the tangential speed's changing with respect to time, which means then we have some sort of tangential acceleration as well. So we will then have a tangential acceleration, which we'll call a sub t. And a sub t, well, again, is going to depend on what the angular acceleration is and the radius of the curved path that point is making through space. All right, so ultimately, what do we have here? The tangential quantities are exactly the same as the translational quantities. The difference really is a matter of being able to discuss different points on a rotating object. So just in general, for tangential quantities, regarding object confined to a circular path, we have that, well, S is equal to r theta. That's just the distance it travels. S equals r theta. And then we've got ourselves the actual v sub t, tangential speed is equal to r omega, and a sub t is equal to r alpha. So we don't want to put delta x here because it's not a linear quantity. It is a distance that it travels for a particular arc length, but, for a particular angle. Arc length is the distance it travels. But we can just throw that in there in terms of distances. So that's really all that we've got going out of this. From all this, we can make the connections that v sub t is equal to ds by dt, and a sub t is equal to dv sub t by dt, making the direct connections assuming that r is constant. That doesn't even need that assumption there. we start messing. But we're going to be keeping R's constant anyway for this course, so there's some other things that we could just say about it. So what can we do with this? Well, again, now we can discuss different points on an object that are rotating, a rigid object, and discuss their tangential quantities. So take this little for instance here. I've got a nice little ruler here, and I've got a blue piece of tape, I've got an orange piece of tape. I'm going to say that this is the axis of rotation down here on this end, kind of hinged there. This is a rigid object that undergoes the same angular displacement as a whole over the same time interval. I rotate it from here to here. Every point on this moved through the same angular displacement. And thus, every point on this extended object had the same angular velocity at any given moment in time and underwent the same angular acceleration. However, in terms of the tangential quantities, that is not true. We can't say it's the same everywhere. For one thing, this piece of tape and this piece of tape, those 2 points on this, and moving this a quarter rotation, move vastly different distances, right? Well, the radius for the blue tape is much, much smaller than the radius for this orange piece of tape. And if we think about a quarter of a circle, well, this one moved through a much greater distance. A quarter of the circumference for a much greater radius than with respect to this one. So there's definitely a difference in the arc length that is correlated with the angular displacement. Now likewise, because there's a difference with those, and tangential velocity is the rate at which the arc length changes with respect to time, well, we can look at this. Even though everything has the same angular velocity, because these 2 points move through different distances in the same amount of time, they have to have different tangential speeds. They're moving through space at different rates. This one moves a vastly larger distance in the same amount of time as this one. So what does that mean? This one on average has to be moving much faster, or relatively faster, because it moves through a larger distance in the same amount of time. And likewise, there's the hinged aspect of the tangential acceleration then. We have that the further away something is from the axis of rotation, the changes that the object undergoes in terms of its rotational characteristics have different impacts on the actual tangential acceleration that correlates with the changes in its rotational state. So the main point with this is, when we start talking about rigid objects, we start talking about tangential quantities, well then it's really a matter of where on the object are you concerned about. At the end of the object, somewhere in the middle, somewhere really close, I look at this point right here. This little point just had to move a little tiny distance in the same amount of time that this point moved this whole distance right here. Much different changes, right? Much different tangential speeds, much different tangential accelerations that the objects underwent, or the points on this extended object underwent. So that's why we want to focus a little bit on these tangential quantities, so that we can have appreciation for not just translation, but point objects undergoing rotation, speeding up, slowing down, or just looking at an extended object, extended rigid object, and different points on that object undergoing rotation. So that's great. We got ourselves some tangential quantities. Is that it for rotation? Definitely not. So at this point, we want to ask ourselves something else. Yeah, we've got some tangential quantities. Are there any other types of acceleration? What if I say that an object is actually rotating at a constant angular rate? So we'll just say that this object right now, this point mass that has some radius of curvature, is rotating with a constant omega, constant angular velocity. What does that mean? That's right. That means that the angular acceleration is 0. No angular acceleration. If the angular acceleration is equal to 0, well, the tangential acceleration has to be equal to 0 as well. Its tangential speed is constant if its angular velocity is constant. So what? Well, ask ourselves, is there any acceleration then? And you may at first say, no, you just said there's no acceleration. There's no angular acceleration, there's no tangential acceleration. I want to know, is there some other acceleration though? Some other acceleration that is necessary? And the answer to that is, well, yeah, let's think about what the definition of velocity is. It's the rate change of position, right? Well, let's also think about what the definition of just acceleration is in general. It's the rate of change of velocity. Well, we ask ourselves, is this object changing its velocity if it's rotating at a constant rate? And the answer is yes, it is changing its velocity. It's not changing the magnitude of its velocity, which would be v sub t, the tangential speed, but it's changing the direction that it's moving in, continuously changing the direction. Velocity is a vector, there's a change in that vector. Even if the magnitude remains the same, the angle's changing with respect to time, there must be an acceleration that accounts for that change in direction. So that's what we want to find now, is what is that acceleration? How can we extract it from a system and quantify it? So let us do just that, because this is a good one. All right, so we're going to take ourselves, similarly to this, some point mass. We're going to say that it's rotating at some radius from an axis of rotation r, and that it's rotating with a constant angular velocity. And then we're going to ask, what is the acceleration on this object? So we want the acceleration of a rotating object. It's a rotating point mass. Under constant angular velocity. All right, so let us take a look at this. We're just going to take ourselves an axis of rotation. Great. We'll take a nice little radius here. We'll take our point mass like as such. And we note that this object will be rotating with a constant angular velocity. Thus, the angular acceleration is equal to 0. And this object will be going around in a nice circle. Not too bad, but that's kind of its circular path here. And what we can start looking at is, well, connection between where it is and what else is going on. So I'm going to go ahead and overlap a coordinate system in here. I think it's best if we just go ahead and use some blue. Sounds good. Let us say this. We've got some X and we've got some Y, just so we can track where this object is. And we're going to start here at t equals 0. And we note that this here is the radius of this curved path that it's going to make. And let's see, let's say that sometime later, it's at some different position. And think about what that really means here. So sometime later, this object will be here. It will move through some arc length like this. This is still the radius right there. There's an arc length that it moved through. And we've also got this going for us. We've got right here the tangential velocity. And the arc length is drawn a little bit suspectly. Right here we've got that the tangential velocity, v sub t hat, is like this. Don't really need the arc length there. And then over here, again, tangent to the path, v sub t is pointing like that. And we could really draw this out at any given position, but we've also got this right here. This is some delta theta, where that delta theta occurred over some time interval that's dictated or connected back with what the angular rate of our rotation is. All right, so let us first try to get an appreciation of being able to track where this object is as a function of time. So where is the object? Where is the mass? It's a function of time. Well, at any given moment in time, this object has to have some coordinates. We went ahead and threw in an XY Cartesian coordinate system. When it's at this position, it has some X and it has some Y, right? So we could say, well, when it's right here, we have some X value and some Y value that it occupies. We can call this just like some X1 and some Y1, just to call it something. We can say, well, what are those two coordinates? Well, first off, what are the coordinates of it when it's at this position at t equals 0? At t equals 0, we have that. The mass is at the coordinates x1, nope, just xy, excuse me, xy is equal to, well, x is going to be equal to r, and y is equal to 0. r, 0. All right, so that's where it initially is. And then, at time t1, the coordinates are xy is, not really equal to, goes to, say, goes to, well, we've got an x1, y1, that are these. So we're saying that this is at t1, sometime t1 that we're just correlating with, hey, it's at a different position. So how could we really represent what these quantities are? Well, in terms of coordinates, that's pretty easy. You say, oh, x1, y1, and r0. But what is x1 and y1 in terms of things like r and maybe this delta theta here? Well, let's see here. We've got r and theta, and we've got an x1, y1. What's the x correlation with polar coordinates? It's going to be r times the cosine of theta. Really, r times the cosine of theta, based upon this being theta is equal to 0. So we have that x1 can be r1 times the cosine theta 1. I'm going to take this little delta off because we're starting at theta is equal to 0 here. So theta 1 is the same thing as delta theta. Confuse things too much there. So there's what x1 is. x1 is r1 times the cosine of theta 1. What's y1? Well, y1 is going to be equal to r1 times the sine of theta 1. So we get the correlation between these coordinates here and, well, these other aspects of it, what r is and what theta is. Well, does this really hold up for this right here so that we can make sure of things? At t equals 0, we have that theta is equal to 0 degrees, and we have that r times the cosine of theta, comma, r times the sine of theta goes to, well, r times the cosine of 0 is r times the sine of 0 is 0, and we got r 0. So ultimately what we get here is just a nice representation of being able to say what the coordinates of this object are based upon the angular displacement that it's undergone relative to theta is equal to 0 and the radius of its rotation. So we have that at any time we can write the ordered pair xy, its position, as r cosine theta, r sine theta. But where's the time in there, right? Where I don't see any time. R is not changing with time. What's changing with time? theta is changing with time. So that's what we need to extract out of this, and then we are on our way to good stuff. Theta depends on time. How does theta depend on time? Well, we can go back to equations of motion for constant angular acceleration. Delta theta is equal to 1/2 alpha t plus omega I times t, but we've already said that alpha is equal to 0, which means that delta theta is equal to omega I times t, where omega I is equal to a constant, and theta initial was equal to 0 degrees. So what do we get with this? Well, from this, we have that theta as a function of time is just equal to omega times t. Angular position as a function of time. So, what can we do? Well, now we can write out what the position is as a function of time in terms of an ordered pair. So we have xy can be written as r times the cosine of omega t, comma, r times the sine of omega t. And we can make sure that this all works out. When t is equal to 0, that's equal to 0. Cosine of 0 is 1, which just gives us r. We throw in a 0 over here for t, and we are at this position right there. What happens when omega t is equivalent to pi over 2? Well, when this is equivalent to pi over 2, the object will be right up here, moving that way, and we will have that its position should be 0r, right? Well, if we put in that omega t is equal to pi over 2, that's going to be equal to 0. And if we put in omega t is equal to pi over 2, that's going to be equal to 1, which gives us 0r. Why would we say it's equal to pi over 2, or how is it equal to pi over 2? That depends on two things. It depends on what the angular rate of rotation is, and it depends on time itself. But we can always correlate the angular rate of rotation and time to some angular position. And that's the point with doing this right here. So what we want to do now is go ahead and say, yeah, we've got really its position in the x, its position in the y as functions of time. Maybe we can use that to get what the speed in the x and speed in the y directions are as functions of time. Well, indeed we can. Let us get components of the object's velocity. As functions of time. So let us just go ahead and throw that up there, back over here. Back a little bit, there we go. Okay, so this is what we ultimately know, that this object's gonna occupy different locations in space at different moments in time, and will have some sort of tangential velocity at those moments in time. And that's it. We want to be able to figure out what is that tangential velocity. And we should be able to note that v sub t hat can be written in terms of a v sub x I hat, comma, v sub y j hat. Or we could say plus vxi. Probably better just to do that. Let's do it like that. An I hat and j hat component added together. So what we want to be able to do is figure out what this I hat and j hat component are. What do they depend on? They depend on what the actual position vector is, which we could write that r hat, the position vector, is now equivalent to r times the cosine of omega t I hat plus r times the sine of omega t j hat. Instead of writing it as an ordered pair, we can write the total position vector as such. So we got the tangential velocity vector, we've got the position vector. What do we have? Well, we've got ourselves that v sub t hat is the rate of change of position with respect to time, right? That is what velocity vector is. So what happens if we just go ahead and start taking the derivative of the position with respect to time? Well, we've got ourselves that this is equal to d by dt. We need this there. Take that off. D by dt of r cosine of omega t I hat plus r times the sine of omega t j hat. All squeezed in there. But there we go. Can we take the derivative of that? Of course we can. We've got the derivative of this. Well, we've got the derivative of cosine is going to be negative sine, and then we got this interior here. We've got an omega t, take the derivative of that with respect to time, and we get an omega out front, and we get ourselves that v hat sub t is going to be equal to negative r omega times the sine of omega t I hat. And then we've got this portion right here. We've got the derivative of sine as cosine. We've got the derivative of omega t as omega. And we get ourselves a plus r omega cosine of omega t j hat. So there is our velocity vector written in unit vector notation as a function of time. Let's check a couple things out here to make sure things correlate with what we expect. Number one, we expect t equals 0, that the velocity vector only has a positive j hat component. It's moving straight up at that moment in time, at t equals 0. That's the direction of its tangential velocity. So we stick in t equals 0 here. We stick in t equals 0 here, this vanishes. Sine of 0 is 0. We stick in t equals 0 here, and we get r omega j hat, which says that the speed of its r omega, and it's moving in the j hat direction. Well, what is tangential velocity equivalent to? R omega, that's right, radius times the angular rate of rotation. So we retrieve something that is familiar. Let us go and say, well, what about like when it's, let's do here. What about when it's there, after it's undergone a rotation of pi over 2 radians? Well, this is, again, omega t is theta. So let's say that this is pi over 2 then. Pi over 2, it's at that position right there. And what do we have? Well, we've got the sine of pi over 2 is 1, which leaves us with negative r omega I hat. And then we've got the sine of pi over 2 is 0, that goes away. And we are left with that the velocity vector, tangential velocity vector, is equal to r omega in the negative I hat direction. That's the negative I hat direction. The speed of it is still r omega. It's moving at a constant tangential rate, but it's changed its direction. Now it's in the I hat. We could go through any position and figure out what its explicit I hat and j hat components of its velocity vector are, and see that at any given position, the magnitude of that tangential velocity will remain r omega, because there's no angular acceleration, no tangential acceleration, constant angular velocity, and it's constant tangential velocity. So we're getting there. We're getting there. We're not there yet. We've been able now to figure out what the function is that describes the tangential velocity with respect to time. So last step, well, we know this is changing with respect to time, directionally. Thus there must be an acceleration. So let us see, it can't be tangential acceleration, right? Because we already said that that has to be equal to 0, because alpha is equal to 0. It has to be some acceleration. So if there's only one thing that's left to do really is say, well, let's figure it out. Let's take the derivative of this and say that the acceleration vector is defined as the rate at which the velocity vector changes with respect to time. And well, we're looking at the tangential velocity here. So we've got that this is then equal to time derivative of negative r omega sine of omega t I hat plus r omega times the cosine of omega t j hat. We take the nice time derivative of that. Well, again, we've got an interior function here. We'll get another factor of omega here, another factor of omega there. We've got the derivative of sine is going to be equal to cosine. So this will change the cosine, negative sine stays there. This cosine will change to negative sine, so this will become negative. And we've got this, we've got the a hat is going to be equal to negative r omega squared times the cosine of omega t I hat minus r omega squared times the sine of omega t j hat. There is the acceleration that is definitely non-zero. It's changing with respect to time. Well, let us take a little bit of a look at this. Let's look at its direction at some different positions in space. So let's say, again, t equals 0. What is the direction of this acceleration vector here? We're sticking 0 here. There is no j hat component. Sine of 0 is 0. We stick in 0 here, and we get that the acceleration is negative r omega squared I hat. So it has a magnitude of r omega squared and is in the negative I hat direction. What does that look like? That looks like an acceleration. It's like that. There's our a hat. Well, that seems weird. The acceleration's that way in the negative I hat direction. What's the acceleration when theta is equal to pi over 2, when it's up here basically? So omega t, say that's pi over 2, so it's up at that position, r0 on the y-axis. Well, this is going to be 0, and we are left with, well, this being pi over 2 is equal to 1, gives us negative r omega squared, j hat. So it's in the negative j hat direction and has a magnitude of r omega squared. Now it's pointing straight down. Well, it turns out that no matter where we look at this object's acceleration, in this particular case, it will always be pointing directly towards the axis of rotation. No matter where it is, this is the direction of its acceleration vector. So, how do we explain this? Come to terms with it. Again, this acceleration is what is responsible not for changing the speed of the object, but for changing the direction that the object is moving at. So initially this object's moving up, but it has to start moving that way. What does that mean? Well, there's an acceleration inward that's pulling it in that direction. And as it continues to change its direction that it's moving at, this acceleration has to continue to change its velocity towards the center. That doesn't mean that it starts moving towards the center because this object's moving around. But it's changing its direction towards the center of this. The reflection is always ultimately kind of like an inward direction. So this acceleration is the acceleration necessary to change the direction of the object. And we call it the centripetal acceleration. All right, so we define this acceleration as the centripetal acceleration. Which is the acceleration necessary necessary to produce a curved path. Anytime something has some curvature to its path, there is some centripetal acceleration. For a circular path, that a hat sub c is going to be equal to r omega squared and is directed inward. Because we're sticking with circular paths, actually it doesn't need to be circular. If it's not circular though, then omega is going to be a little bit careful with that. You've got radii changing. So we're going to keep things circular, standardized radii, and we can define centripetal acceleration like this. Centripetal. So this is centripetal acceleration. We'll call it a sub c. Always directed radially inward. Centripetal means center seeking. And again, it's the acceleration that correlates with curvature of an object's path. So there's a couple things with this. We said that the only thing that this acceleration is doing is changing the path of the object, not changing the speed of the object. Is that really true? Is that really true? Well, let's take a little look at this. Let us look at the magnitude of the tangential velocity. Well, we had this. We had that v sub t hat was negative r omega times the sine of omega t plus r omega times the cosine of omega t. That's j hat, that's I hat. It's 0, going straight up. Pi 2 is negative, yes, that's right. So, how do we get the magnitude of this? The magnitude of a vector is the square root of the sum of the squares of its x and y components, right? So we've got the square root of r omega sine of omega t, quantity squared, plus r omega, there's a negative sign there, sorry, r omega times the cosine of omega t, quantity squared. So here's the magnitude of it. Well, let's look at this. We've got r squared omega squared, negative sign goes away, r squared omega squared, two terms of that, so we can write this as just being equal to, take the square root of the r squared omega squared, and we got that, multiplied then by sine squared omega t plus cosine squared omega t. What is this equal to? Sine squared omega t plus cosine squared omega t just equal to 1, which then says that that tangential speed, the magnitude of the tangential velocity, is r omega. That's it. It's constant. If omega is constant, omega is changing, the tangential speed changes. Fantastic. What about the magnitude of the centripetal acceleration? The magnitude of a sub c is going to be equal to, well again, the square root of the sum of the squares of the x and y components. It's a little bit different, but we've got ourselves a negative r omega squared cosine of omega t squared. So there was the I hat component. We've got a plus r omega squared sine of omega t, the j hat component. And what do we do with this? Well, again, this becomes positive, positive, r squared omega to the fourth, r squared omega to the fourth. Common term, we can factor it out, take the square root of r squared omega to the fourth, gives us r omega squared, and we've got ourselves magnitude of the centripetal acceleration is r omega squared. And, well, again, we've got this cosine squared omega t plus the sine squared omega t, which is just equal to 1, which says that that is the magnitude of the centripetal acceleration. Constant as long as omega is constant. Change omega, hey, you change the centripetal acceleration. You require a different acceleration to constrain an object to a curved path. The faster an object's moving, the greater the acceleration inward must be in order to continuously change its curved path or change the direction of its motion. The larger the radii of curvature, the greater the centripetal acceleration is for continuously changing its direction inward. So we've got that going for us. Great. What else goes with this? That's pretty good for the centripetal acceleration. What we have now is the ability to talk about an object's total acceleration, because centripetal and tangential are perpendicular with respect to one another. And whenever we have two vectors that are perpendicular to one another, we can talk about them separately. So, we can now consider an object that is rotating in a circle under an angular acceleration alpha. So we can take again an axis of rotation, some point mass, radius of rotation, and say that alpha equals some constant, that it's not 0. Constant not equal to 0. This object then will have some accelerations, right? Well, that means that a sub t then is not equal to 0. And if this object's moving in a circular path, well, there has to be a centripetal acceleration. So if we start drawing some stuff in, we will have some centripetal acceleration directed inward towards the axis of rotation, and we will also have some tangential acceleration that is ultimately correlated with the angular acceleration of the object. So we'll have these two accelerations, no matter where this mass is. The orientation of these two accelerations with respect to one another will remain the same. But if we have the alpha is equal to a constant, that means that the tangential acceleration is a constant. So even though this is changing its direction, it will be tangent to the path. It does not change its magnitude. However, if this object is speeding up, we'll say, speeding up in its rotation, well, what's happening then with the magnitude of the centripetal acceleration? If it's going faster and faster, the angular rate is changing, which means then that the centripetal acceleration's magnitude must be changing as well. So that means then that that would be getting larger. But again, there's a 90-degree angle in between these two. So if we want to define a total acceleration vector, it is going to be the vector sum of these two individual accelerations. It's the only accelerations that there are. So total acceleration vector for a rotating object is the sum of the tangential and centripetal accelerations. So the direction of it is really a matter of where is the object and what do you want to reference the direction with respect to. We'll get to the direction in a moment. If we want to just know what is the magnitude of the total acceleration vector, the magnitude of the total acceleration vector is going to be the square root of the sum of the squares of the tangential and centripetal. So t squared plus a sub c squared. Could we go ahead and figure out what that is? And the answer is, yeah, of course we can. Because we know that a sub t is equal to r alpha, and we know that a sub c is equal to r omega squared. So what can we do with this then? Well, we can write that the total acceleration vector's magnitude, overall acceleration's magnitude, is then equal to the square root of r squared alpha squared plus r squared omega to the fourth. Where, yeah, you could definitely factor out an r there because it's a common term in both of them, r squared. So this is something that can be played around with. Now, if alpha is a constant, this particular portion is a constant, but omega is going to be equal to alpha t plus omega initial, right? Constant angular acceleration, that is omega as a function of time. So in the end, it's a little bit big, but not that bad. We get that the total magnitude of the acceleration can be written as alpha t plus omega initial to the fourth. And again, you can start factoring some stuff out, playing around with this, but there's how we could write out the total acceleration vector's magnitude in terms of the constant angular acceleration, a particular moment in time, the initial angular velocity, and the radii at which this object is rotating. That's important. What about the direction of the total acceleration vector? The direction of the total acceleration vector is really a matter of what do you want to reference with it with respect to. So again, we can take two vectors that are perpendicular with one another and figure out what the total composition is, right? We would have a vector that goes, that one's pretty badly drawn, but say like this. Here is a total hat. Over here, the total hat. Let's just translate the vectors, right? Tail to tip, and draw on the vector that correlates with them. Now, in terms of the direction of this vector, it's really a matter of what do you want to reference it with respect to. Generally, you will likely find that it's referenced with respect to the radial direction or the centripetal direction, but just as well we could reference the tangential direction. But I'm just going to go ahead and say that this is some angle theta. Angle theta, those are two different thetas in this particular case because the centripetal acceleration is changing. So we can call this theta 1 and theta 2. But ultimately, if I want to get what that theta is, we think about tangent of opposite over adjacent. And we can write the angle A hat total as theta is equal to arctangent. Again, opposite over adjacent will be a sub t over a sub c. And that is with respect to the direction of a sub c. To say with respect to the radial direction, radially inward. there we go. That's how we get the angle. Reference it with respect to some standardized direction. Radially inward is a nice standardized direction. And that's what we've got. So, yeah, that's some good stuff right there. Something else goes with this. Piling it on. Do a little recap here momentarily. We can then define centripetal force. I'll say now define. Centripetal force, which is the force required to constrain an object to a curved path. F sub c is equal to m times a sub c, which then gives us that the magnitude of the centripetal force is going to be equal to mr omega squared. But we can also write that v is equal to r omega, which gives us that omega is equal to v divided by r. So we could just as well write this as mv squared over r, where this is the tangential velocity, the speed of the object. And there we go. It's always directed radially inward. And there is its magnitude, the force required to constrain an object to a curved path. So I take something, again, like this little point mass here, and I spin it around. I say, well, something has to be responsible for producing the angular acceleration that correlates with the change in the velocity vector. What is that? Well, that's a force, right? Forces produce acceleration. So there has to be some force acting on this object that ultimately constrains it to this curved path. What's acting on this object? Well, look at the strings attached to it. The strings pulling it radially inward, completely or continuously constraining it to this curved path. So in this particular case, the centripetal force is gotten through the force of tension in this string. The centripetal force just depends on the system itself. What happens if I take like a little ball here and say, I want it to spin around in this bucket? If I can take this bucket and I can get that ball so it's spinning around, you say, well, what force is acting on this ball that's constraining it to its curved path? You say, oh, that's got to be the normal force. The normal force is pushing it inward as it rotates around, perpendicular to the surface of contact between, well, the bucket and the ball. You go drive in your car and you go around in a circle or turn the corner, guess what? There has to be some sort of centripetal force that allows you to actually produce that curvature. What does that force do to? Friction. Force of friction allows that to occur. You're driving down the road and you want to make a right turn, and guess what? There's no friction, and you turn your steering wheel, the road's really icy, you just keep on going straight because there isn't the friction required to substantiate the centripetal force that allows the curvature. So again, the centripetal force really depends on the system in terms of what is producing the centripetal force, but this is how we quantify the centripetal force. mr omega squared or mv squared over r. It depends on angular rate of rotation and the radius at which that occurs at, and the mass as well, as it should. So there we got some centripetal force, centripetal acceleration, and let us just rewrite all of this stuff down real quick, and then we'll consider doing a nice little problem that looks at some of this stuff. And we'll just spell out again what's important here because there's lots of stuff going on. And in the end, we want to know what we need to concentrate our attention on. So we got ourselves tangential quantities. We've we've got ourselves that S is equal to R, we should really get delta theta. We've got that V sub t is equal to R omega. A sub t is equal to R times alpha. Tangential velocity, tangential acceleration, arc length, the distance something travels. And then we had ourselves centripetal quantities, which really just correlate with centripetal acceleration. A sub c hat is equal to R omega squared, which can also be written as V squared over R via the tangential quantities here. And it's radially inward, and we've got ourselves F sub c hat is equal to mr omega squared, which is equivalent to mv squared over r, radially inward. Total acceleration for constant angular acceleration. We got the magnitude of the total acceleration is equal to the square root of r squared alpha squared plus r squared times alpha t plus omega initial quantity to the fourth, not squared, excuse me, fourth, and theta a total. It's got my arctangent of a sub t over a sub s. With respect to the direction of a sub c. And that's pretty much that. All right, let's look at a problem, shall we? We shall.